Right, so we're looking at this SD plus here. Um, that's what they call it because it just adds on to it if you think about this. So we're going to look at a couple examples where if you do your measurements -1, and then you take the square root of that, it's going to be just barely above 1. And so if you times a number that's just a little more than 1, then it's going to increase just a little bit. And that's why they use this. If you think about that distribution that we had drawn up, that's why they do this. So this is what the textbook uses, this symbol, this SD plus. This symbol right here is what your calculator uses, if you want to think of it that way. But you can use this formula. Either way, if you use your calculator, that's what it is. And I'll show you an example of both here in just a minute. Okay. So that's the first problem. So let's just practice on that really quick. So if we've got an exam that has 10 exam scores, again, that's a small sample size with a standard deviation of 14.5. Calculate that SD, we just take the square root of 10 over 9. Remember, we don't want that. That's the only thing we want in the square root. And then we're going to times that by the standard deviation, 14.5. And when we do that, that gives us 15.28. So you guys can see that standard deviation just increases just a little bit. And that accounts for that being just a little bit smaller. That's it. Okay? Pretty simple to do that. The second problem we have with this is the sample sizes that we have are small, and so we don't really get the full power of the central limit theorem. So if you guys remember, this first one is the histogram of the actual Gettysburg Address, and remember how skewed it was. But the way we accounted for that was by having multiple samples, multiple trials of that sample, and that helped us with what we call our central limit theorem. Even if we only take like let's say 10, it's still going to give us, it gives us a histogram here. If you notice, it's pretty good, but it's still got a longer tail here to the one side. And so the data must be normally distributed or symmetric to begin with. So using a T distribution instead of a normal distribution helps us with this. So let me just show you this. This is, let me just explain what this is. This red line is the normal, standardized normal distribution. So if you notice, it's at 0 here. Again, it's the standard normal curve. And then the blue one is what we call a T distribution. Okay. And so if we actually want to look at this, we can actually change this. If you notice, there's a lot of difference down here in the tails, right? And that's because of that small sample. The small sampling size leaves this uncertainty in the tails. Just don't know exactly what is in this tail and how much. And so that's why that's changed. So the blue line again is the T, and then the red is the normal curve. So just to give you guys an idea of this, so I've got this, what they call these degrees of freedom. Degrees of freedom, all that is just when you take your sample size and you minus it by 1. Okay, so that's our degrees of freedom. So look here, if we actually drag this out to where we're at. So notice how when I get a higher degrees of freedom, which is a higher sample size, see how it becomes more and more like the normal curve. Even at 10, which we did with our Gettysburg, there's still a little bit of space here in between the red and the tails here, red and blue. But notice when this becomes even closer. You guys notice, look here, at 30, at 30, we are almost identical. And so that's why we say it, when you have a sample size of 30, then you can just use your regular one tail that you guys did last week. So if you drag this out even more, look, by the time you get to 40, it's almost identical for sure. But that's why that should give you hopefully a visual. So we're going to use this, what we call this t-distribution, which is just a little bit more uncertainty in there. And that's one of the issues that we have with this. Okay. So those are our two problems, and that's how we're going to account for them. We're going to use the SD plus, and then we're going to use the t-distribution, which accounts for this, depending on how big our sample size is and how many degrees of freedom we have. Okay. So again, just to reiterate this, we are just going to our student curves are similar, but the tails are a little bit different based on those two. And then we're going to use these degrees of freedom. Degrees of freedom is the number of measurements or number of draws. Draws is the same thing as measurements in statistics. We're going to -1. And then we're going to use our calculator on there. Our calculator has a function called TCDF, where we're just going to use our lower bound, upper bound, and degrees of freedom. And that'll tell us the area under a T curve. So TCDF helps us with T curves. Okay. So we've been using normal CDF, but we're going to use that just a little bit different there. Okay, so let's just practice really quick with this on our calculators. So we want to, for this one, we do TCDF, and then we are going to go our lower bound. So if we're going degrees of, or we're going to the right of 1.9, and you can draw this. I know it's a little bit different, but you can draw it like a normal curve. With it's been standardized. Zero's right there, 1.9, and we want to the right. So this is our lower bound. So we go lower bound 1.9, upper bound is whatever your favorite upper number is, so 500, and then we just need to put our degrees of freedom. Okay, and I'll show you this on a calculator in just a second. And so what do we get there? Oh yeah, and we're going to times this by 100%, and so we get 4.7%. This next one, we have 20 degrees of freedom, and we're one on the left of negative 1.36. So again, 0. We're down here at negative 1.36. Want to go to the left, so we'd go TCDF. Our favorite lower bound, which would be like whatever, negative 500, to our upper bound, which is negative 1.36. And then the degrees of freedom, which are 20, and we get 9.45. Okay, and that gives us that value right there. So let me just show you this on the calculator really quick. So on our calculators, we're still going to go to this var, this distribution. So we'll go second vars. And then if you notice, TCDF is option number 6 here. Okay, right there. So we hit that. We're going to hit our lower bound. On the one, it was when we went from 1.9 up. So we'd go 1.9. We go our upper bound, which is our favorite big number. And then our degrees of freedom on that first one was 8, if you're looking at the slides. And we just hit enter, and it'll give us this. If you times this by 100, then it gives you the 4.7 that we had. Okay, and then that second one, again, we just go second var. We go to option number 6 here, and our lower bound was the negative 500, or your favorite low number. And then our upper bound was negative 1.36. And then my degrees of freedom were 20. Again, these were the two that I just did, just showing you on the calculator. Hit enter. If you want to times it by 100 before, you can. And we get 9.48 or 45. Okay. So that's how you get that done on your calculator there. Okay. All right, so hopefully you guys are good with that. We're using that instead, okay? So our t-tests. So our t-test is used for quantitative problems and small sample sizes. So average questions is what we're going to look at. with these. And our sample size has to be less than or equal to 3 or 30. So anything lower than 30. We're still going to construct our null and alternative hypothesis using the same rules as we have before. The only difference that we're going to do is on our t-test, we're actually going to use the standard deviation plus for calculating our SE average. Okay, and then we're going to still, instead of, we're going to call it a t statistic instead of a z score, a t score. That's the only difference here. Okay, this should look really similar except we're using that SD plus, and then we're just calling it a t score instead of a z score. And then we're still going to find our p-value. We are going to use this idea. We got to find our degrees of freedom by taking the number of draws. So you just need to remember this part here, that this is the number of draws minus 1. Okay, and then we're going to calculate our p-value by using the TCDF, lower, upper, and then degrees of freedom times 100. And then we'll draw our conclusions with the same rules as z-tests. Okay, so meaning we're still going to use that 5%. That 5% is still going to be our cutoff. We still are going to use that. All right.